Okay, good evening, everyone. Welcome to our monthly IEEE Women in Engineering talk. I am Nusrat Islam, Women in Engineering Group Chair. First, thank you everyone to attend tonight. The goal of this program is as a mission and vision of IEEE Women in Engineering to promote women engineers and scientists and inspiring girls around the world to follow their academic interests in engineering field. I'm so pleased to be with you tonight and to have the chance to introduce our guest speaker today, who is going to talk to us about a journey towards becoming LANL scientists. The speaker will touch on the science she discovered along the way. She will also talk about some of the aspects of the journey and try to impact what advice she can give to others who wish to pursue careers in STEM. Our speaker earned her Bachelor of Science in Astrophysics from the University of New Mexico. She obtained her master's degree in physics with a thesis under Dr. Mark Gilmore. After her PhD in electrical engineering from UNM, she joined as a postdoc at Los Alamos National Laboratory. After doing research for 2 years on the Omega and NIF laser facilities, she now became staff at Los Alamos National Laboratory. We shared same lab during her PhD life and my master's. So I know her personally. She's a great electrical engineer. So without further ado, please join me in welcoming our tonight's speaker, Dr. Tiffany Desjardins.
Thanks, Nusrat.
Yes, so just before we begin, I request everyone to make sure your microphone is muted. Please use chat window to type any questions, comments, any suggestions would be appreciable. And you are most welcome to unmute yourself if you want to ask any questions. All right, Dr. Tiffany, the floor is yours.
Thanks. So thanks for everybody being here. Thanks for inviting me. This is actually a first for me on many aspects. I've never given a talk geared towards other women. And so when Nusrat asked me, I felt like, yes, I really want to say yes. I want to support women in STEM. And then, we were talking about what I should talk about, and she said, it's really be great to have a talk that inspires women in STEM. And I was like, wow, I don't actually know what that looks like, because I only ever go to technical talks. And so I tried to think back to when I was younger and what would I have wanted to see in a talk like this. And for me, I came from a background without much science or engineering in it. And it would have been really great to have known more what the possibilities are out there for women in science and engineering. And I'm not really comfortable talking about science I don't know, so I decided that I'd tell you guys a bit about how I ended up where I'm at and try and focus on the science so that you guys can get an idea of what's out there, and maybe my journey helps some of you at the same time. And so I've never given a talk like this, so we're going to see how it goes. So I am from a state pretty far away from here, all the way on the other side of the country, Pennsylvania. And I grew up in an incredibly small farming community. So people there didn't really do a lot of science. My high school for my senior year, I had AP chemistry and AP bio. Those are my only choices for my college science classes. And I think we had one physics course in our high school. And so I knew enough about myself to know that I wanted to go explore. I wanted to study things nobody else had studied before and try and solve mysteries that we didn't understand. And in my head as a kid, that meant being an astronaut, right? I was like, we know everything there is to know about Earth and being on Earth. So let's go away from Earth. And this is how I remember this conversation going with my father. I was like, hey, Dad, what do astronauts go to school for? And I remember him kind of grumbling and being flabbergasted that I was asking him this question. And he was like, well, anything science related. You can be a chemist, you can be a biologist, they need all types. And in true high school student logic, I was like, no, don't be silly. Surely astronauts go to school for something like astrophysics, because astronauts and astrophysics have the same first few syllables. And so that's what I said I was going to go to school for. And of course, back in those days, Google search wasn't a really big thing, so I didn't really know what I was getting myself in for when I chose this. And I want to put this at the beginning. In my career, I've talked to a lot of women, and I've come to realize that I was really lucky. My family did not tell me I was insane. They did not point out I was female, and this wasn't something most females go to school for. And I only remember one person who said to me when they found out I was going to school for that there was no way I was ever going to get a degree in astrophysics because they had failed out of an electrical engineering degree. And they were there, and they obviously were smarter than me. And so I feel really lucky and blessed because I've heard so many stories from women who have had criticisms and who have faced the opinions and had to fight the opinions that they can't do it. And I wanted to put this at the front as I go through my story, because I do feel really lucky and blessed in the people that I've had to support me. And if you're one of these women who is here, who has faced these criticisms, I'm really sorry that you have faced these. And I want to tell you that, yes, you can do it. It might be a struggle. You might question it every day. I question it still every day. I have my PhD in electrical engineering. I do experimental physics. And there are days where I still feel like, oh my God, I can't do this. But then, you take a deep breath and you get up the next day and you try again. And I want to tell you, don't listen to those people who tell you you can't, and to keep doing it if you love it. And if you love it, you can find the strength to keep doing it. So that's just kind of like my at the beginning support for other women here. And so it turns out that if you want something like a degree that specializes in astrophysics, there aren't many places to go who actually offer degrees specifically in this. And so my new adventure post-high school started in New Mexico, and I have never left since I was 18, minus for some internships and work. But and so University of New Mexico is one of the few schools that offers degree in astrophysics. So I went to New Mexico, and I was so excited. I was going to get this degree in astrophysics. Only I never really thought beyond that, yeah, in high school, I'm like, yeah, I want to be an astronaut. And I'm going to get a degree, and everything just magically works out, right? And if you're earlier in your career, or maybe not even so early in your career, you might be trying to think, what comes after, right? You're taking these classes, you're learning all this. And what do you do after you get your degree? How do you figure this out? How do you decide? Like, I never planned to be a LANL scientist. I never planned to even get a PhD. I was like, I'm going to get a bachelor's and that's it. And part of the answer to this is internships. So if you're an undergraduate listening to this, I highly encourage you to find summer internships. If you're a senior graduating even, or a master's student graduating, there are also opportunities. National labs, pretty much all of them, I think, have summer internships, and they accept almost all levels, high schools, undergraduates, for those graduating seniors or masters. They offer postdocs, which are usually one-year appointments where you don't know if you want to go to grad school or if you want to go get a job. So you go take a year off as a postdoc and get some real work experience. Or you don't know if you want to get a PhD. And so you go and apply for a postmaster's. And then this also opens the doorway to other possibilities of the lab. Maybe you don't need one of those advanced degrees to get the job you want at a lab or an industry. If you're an undergraduate, there are these experiences called research experience for undergraduates. And these exist for all sorts of fields. I popped in this, I had to look up what the acronyms stood for, didn't remember, went to their website. They have them for chemistry, engineering, physics. They had one specifically for astronomy when I was younger. And these are really great opportunities to go and see, okay, do I really like this thing I think that I like? And then we also, when I was a grad student, we had lots of undergraduates show up at our lab and say, hey, I want to see what it's like to do experimental physics. And they would come, initially they would usually start as volunteers, and then if things worked out, we would see if we could afford to pay them. And then of course these days you can ask Google just about anything. And it's a little scary sometimes how well it reads your mind, but it can help you find some of these. And to give you an idea, I did 3 summer internships during my undergraduate time and a research project with a department professor to help me figure out what I liked and what I didn't like, and help me find my path forward. And so the first one that I did between my sophomore and junior year was at the National Solar Observatory. And this is probably one of the more exciting ones because this is where I learned about our sun as a plasma. So I'd been taking news astronomy classes, and they kept telling me how boring our sun was as a star. And when I went to the National Solar Observatory, they're like, oh no, our sun is full of really cool physics. In fact, our sun is made of this thing called a plasma, which we usually call the 4th state of matter. And so this graph here shows it really easily why we call it this. You know, most of us think about solids, add some energy to a solid, get a liquid, add some more energy to a liquid, get a gas. If you add enough energy to a gas, you start popping electrons off of the atoms. This leaves behind your positively charged atom, which we call an ion, and then your negatively charged electron. And this is a plasma, and plasmas are made up of these. It turns out that with the exception of Earth, plasma is extremely common in the universe. It makes up an estimated 99% of visible matter in the universe. And it's extremely useful. It's used in industry, and it's all over in astrophysics. So the other cool thing about this internship was this is one of the internships where I had a female mentor. I also had a male mentor. I had one of each. And so what I studied during, or what I learned during that summer, was that the sun cycles between what they call solar maximum and solar minimum. And each of these lasts about 11 years for a 22-year cycle. And what happens is the sun has a magnetic field. Plasmas have this really cool property that if they're dense enough, they trap magnetic fields in them, and the magnetic field gets dragged along as plasma moves. And the sun, as it turns out, is a big rotating ball of plasma, but it doesn't rotate equally everywhere because the plasma is also like a liquid. And so as it spins, the magnetic field gets twisted and kinked, as you can see in this cartoon here. And so this gives rise to things called sunspots, which you can see up in this image here, which look dark because they're so much cooler than the surrounding plasma. And this is actually just places where this kinked up magnetic field has projected out of the sun. This also leads to things like these prominences. So this is a big magnetic field line that has come, millions of miles out of the sun, and plasma is streaming along that magnetic field line. And then you get cool things like coronal mass ejections and solar flares, which I haven't kept up on the science, but at the time the belief was that the magnetic field line would break, and this would allow plasma to eject out. And so there was this project, and I think this is still ongoing, called the Sun as a Star Project, where they were trying to understand this physics. And one of the reasons you'd want to understand this is there's the 2 extremes. So during solar minimum, the sun is cooler, and the Earth actually can be cooler. And believe it or not, people have been observing and recording sunspots since about the 1600s. And there was a period where the sun did not come out of solar maximum when it was supposed to. And the Earth got colder than it had ever gotten before. And this was often dubbed the Little Ice Age. There are all sorts of famous paintings from that time of people ice skating. I think it might have been in the summer at unusual times of the year. The other extreme of this is solar maximum. And during solar maximum, when you start getting all these coronal mass ejections and solar flares, these days, we have all these satellites in space. Well, what happens if a really big coronal mass ejection comes in and wipes out most of the Earth's satellites? That would be very problematic for our current communication in the world. There was actually an incident, I want to say it was in the 70s, I meant to go back and look this up, during solar maximum, where one of these really bad solar flares came in, and it actually knocked out the power grid for like Montreal, and I want to say New York, and a bunch of Northeast cities. And it was just because all this solar radiation came in, and we didn't know it was coming, and we didn't have protections for it. So they wanted to try and see, could we find a way to start predicting when the sun's going to switch between these, or if it's going to fail to switch between these. And this is some of the first steps also trying to figure out, can we start to predict things like when maybe bad solar flares are going to be coming to try and protect our satellites. And so what we did was we used this, so I worked with two advisors. One was an expert in this McMath Pierce Solar Telescope, which is quite old. And the other one was an expert in this integrated solar spectrometer, which they had just recently built. And both of these collect a spectrum of the sun. And what they wanted to do was prove that this ISS was working properly. So once a month for 5 days, we got time on the McMath Pierce Solar Telescope. And assuming that the weather, and this is in Tucson, so as you might imagine, the weather typically behaves. Weather permitting, we could go up for a couple hours a day, and we would have sunlight come in the top of this, down this telescope, and in through the spectrometer onto this grating here, and we would collect that spectrum. And then any day I wasn't doing that, I could sign into the ISS and just stare at the spectrum of the sun and compare those. And so that's what I spent that summer doing, was collecting spectrum data and comparing them to say, yes, these look the same. We can stop trying to get time on this telescope, and we can just start using this telescope full time. So my second summer internship was actually through Los Alamos National Laboratory. And I don't remember how I learned about this. I think an email went out at UNM. And I came away from my first summer internship really fascinated by plasmas. I wanted to learn more. And they had a project in plasmas. And I was like, yes, this is what I'm going to apply for this. And I got it. And so during this one, I learned more about a different type or application of plasmas, which is fusion energy. The fusion energy I'd heard of a bit about because it's what powers our sun, initially anyway. If you start with hydrogen and you condense it, you start getting things like deuterium and tritium, which are isotopes of, I think isotopes of helium, or hydrogen, sorry. And if you force those together, you get helium out, you get a neutron, and you actually get spare energy out. And so fusion energy is believed to be a safe and renewable source of energy, if we can make it work, which is the hard part. And during that summer, I learned about two types of fusion energy. I learned about what's called magnetic confinement fusion, where the most common form of this is what's called a Tokamak, which essentially looks like a donut. And you make plasmas in here, and you try and fuse this deuterium and tritium to get energy out. And then I learned about another type called inertial confinement fusion. And this is what I spent most of my summer staring at data from and just doing image analysis of trying to measure electron temperature and ion temperature of the plasma. In inertial confinement fusion, what they do is they start with these little millimeter-sized capsules. They hit them with high-power lasers and radiation to cause the capsule to shrink from its millimeter size down to about 20 times smaller. Inside that capsule is deuterium and tritium, and then this creates the fusion process. And and I also want to mention that my mentor for this project was also female, which was really great. And so I remember her talking to me a lot about image processing, learning about these types of fusion, which I thought was really great because I was like, oh my, if we could make this work, we wouldn't need to use oil anymore. We wouldn't have to be putting all these pollutants in the atmosphere. Like, this is a really cool application of plasmas. And learning a lot about image processing. And then overlapping with this, I actually started working with a professor in the physics department. And this was a true astrophysics project where we used this radio telescope array that had just come online. It was called KARMA. And I feel like I probably should have put some pictures in here about how this works. But essentially what a radio telescopes do is they stare, you have a big array of them, they all stare at the same point, and they measure the same signal. But because the radio telescopes are at different points, these signals come in with delays and lags. And by comparing those lags, you can do what's called interferometry, and you can get useful data out of this. And I will also admit that's about all that I really remember about how the data analysis of that works. That is the high level. It's been a while. And what we were looking at specifically was a spiral galaxy called NGC 891. And it is this spiral galaxy that we can see completely edge on. And there are all sorts of theories and models about how spiral galaxies should form. And they told us that there should be gas off the plane. It should be up in these regions, a particular type of gas. And so we sat down to try and start measuring it. And as you can see over here in this picture on the right, these contours were our measurements, and we never found it. And unfortunately, we couldn't say whether we couldn't find it because it wasn't there and the models were wrong, or if we didn't find it because our telescope wasn't powerful enough. And that was sort of my year with the professor. And remember, it was a lot of like staring at images on a computer, and I don't really remember a whole lot else about it. So you can kind of tell which projects were really speaking to me as I was going through this. And then between right before I started graduate school, after I'd already finished UNM, I had decided that I was going to get a job, and I found this last-minute posting on San Diego National Labs. And so I went ahead and took it. And it was doing something I'd never done before, computer simulations. And I was like, okay, I know a little bit about what astronomers do. They do a lot of observing. We're going to go try this. And so this project, again, was a really cool application project. So gallium nitride crystals are commonly used in LEDs. And this may seem strange now because I feel like LEDs are everywhere. You know, most of our light bulbs anymore are LEDs in houses. Back in 2008, when I had this internship, they were having a problem. They wanted to go to LEDs because they're more energy efficient, but man, they're really hard to grow. They couldn't grow them in batches very well. They couldn't grow them in large sizes. And so, the Department of Energy runs Sandia, and they were really invested in coming up with moving the world, or the United States, to this more energy efficient lighting source. And so we try to simulate a method for faster growth using quantum electrodynamic simulations. I'll be honest that there was a lot of physics involved in this that I didn't understand. Mostly my mentor sent me what I would call an input deck, which has like all these initial conditions you set up. And I would ship that off to some supercomputer and wait for it to finish and pull it into some visualization program. And what we were trying to do is kind of depicted actually in this image over here, which I found from a 2012 DOE publication when I was looking this up, which was if we put gallium and nitride at two different places in a tank of some other material, could we get them to efficiently bond to each other with this catalyst to help? And that's what we were trying to simulate. And at the end of that summer, my answer was, this is never going to work. Being that they were still working on this 4 years later, I'm guessing they had some good results with this. I maybe should have looked up how they do this, but I'm not really sure how we grow LEDs so efficiently these days, or if we've just gone to large mass production growing these on wafers, which is how they are initially grown, is from one of these gallium nitride wafers. And then we hope that they're pure enough to be used. So, and so that was kind of my experience in that summer one was, again, it was a lot of sitting at a computer waiting and trying things and waiting. And so at the end of all these, I knew a couple things. One, I, to this day, love plasmas. They are complex, they are incredibly useful, they're incredibly confusing, they're really pretty to look at. And they make up this the universe. So how could you not want to study this? At least from my point of view. I also discovered that, and this may not be surprising given how I chose astrophysics, I really didn't like it. I found it really boring and tedious. The thought of spending 5, 10, 30 years collecting all the data you need to try and prove a model or a simulation seems really frustrating to me. And I didn't find it very satisfying. I also couldn't understand why I should care about things like, why isn't there gas off the plane of that galaxy? It doesn't affect anything on day-to-day life. And I didn't really have patience for computer simulations at the time. And so I knew I wanted to do experiments. I wanted something I could touch, I could control in real time. And this is my second piece of advice to you. Find something you're passionate about. Do internships, find what you like. Don't force yourself into a job where or a study of something that you don't enjoy, because the rest of your life is a long time and we spend a lot of time at work. So try to find something you at least like, but I would recommend you're passionate about. And so then it turns out that I was overly ambitious in my choice of graduate schools, and I got into only my backup school, which was UNM, and turned out to be probably the best thing that could have happened to me. I met another woman who was at UNM, and she informed me that we had a plasma program. It was just in the electrical engineering department. And so she introduced me to Mark Gilmore, Dr. Mark Gilmore, who, as far as I know, is still in the ECE department. And graduate school can be a lot of fun if it's what you want to do and you've got a really great group of people. And you can do some really cool things or crazy things. And I had to put this picture in here when I stumbled onto it, was me crawling down this 4-meter long vacuum chamber. And if I wanted to do this at LANL, I would probably spend weeks in training to be able to do this. And they would stick me with a respirator and all sorts of safety gear to crawl down that tube. And all we did was tie a rope around my waist in case I panicked and they had to pull me out. So lots of fun, met a lot of great people, met Nusrat. So what did I do in grad school? So in grad school, I got to go back to plasmas. Only now I got to touch plasmas. Well, actually, you don't touch plasmas, but I got to touch a plasma experiment. And so in the basement of the electrical engineering department is what's called Hellcat, which stands for helicon cathode. And this is a linear plasma device. And so you can actually see this really cool picture. So there's this stainless steel chamber back here underneath these big guys, which are magnets. And it's a vacuum. And we pump it down to vacuum. You backfill it with argon. And then in this case, we use what's called a helical antenna, or a helicon antenna, which is just a helical antenna wrapped around the Pyrex tube. You shove in some radio waves, launch them into this background gas, and it ionizes to make a plasma, right? Pretty simple. I'm not going to go into all these details. I put lots of these details on there for people who are maybe familiar and interested. So why would anybody want to study this? What do you do with this? Why do we care? And so this goes back to fusion, where I had learned about one of my internships, in this case, Tokamaks. And so Tokamaks have been considered one of the most promising sources of fusion energy for decades. And the problem is that plasmas are not stable. And because of these instabilities, when we put energy in to combine that deuterium and tritium to create fusion, the energy doesn't go into combining them. It gets stolen by these instabilities that then put it into turbulence. And this is problematic. And so in order to fix this, you have to understand where all of these come from. So the problem is that tokamaks are really complicated. So a tokamak looks like a donut. It is a donut-shaped stainless steel chamber, typically. One of the big problems with plasmas is they're really hot. And so you don't want a plasma to touch your chamber because you might damage it. Also, when your plasma touches the chamber, it stops being a plasma and it turns back into a gas. And so what we do is we use magnetic fields to what we say confine the plasma. We force the plasma to be more centralized in the chamber. This protects the walls. And by confining it, we also help increase its density. And the denser it is, the hotter it is, the more likely we are to get fusion. Because of tokamaks are this donut, they have to use some really strange magnetic field configurations to keep that plasma in place. And so they actually have these helical magnetic field lines. Now, you might remember when I was talking about the sun earlier, that magnetic field lines can cause some really crazy phenomena in the plasma. You can get ejections of mass from instabilities. And that is part of what we see that happens in tokamaks. And there are other ways to create instabilities in the plasma. So trying to understand not only that, but plasmas also have, what I showed on here in this other image, is they're not actually round. They tend to be more oblong. And then they have these hot, dense regions, and they have very non-dense regions at the edge. So this is a hot, dense core, cold outer region. You know, if these two talk to each other, bad things. But it makes the physics changes when you go from this hot core center to this low temperature, not so dense center. And so trying to understand this as a whole is extremely complicated. And so what you need to do when you have an extremely complicated experiment is you need to break it down into building blocks. And that's where linear plasma device is coming. So we simplify the geometry. We have a simple magnetic field. So we remove any instabilities that are caused by the magnetic field. Because we go to this, we now go to a more uniform density. And so this makes looking at the physics of density gradients easier. And then tokamaks don't have a very high rep rate. I'm really spacing on their rep rate, but it's incredibly slow. They have to allow them to cool down in between shots. My recollection on Hellcat is we shot at like once a second. We could take data. We could literally get, you know, thousands of shots in a day versus I think tokamaks can get maybe a handful of shots in a day. So it makes it much easier to change configurations and see what works and makes a difference. And so and then you're like, well, is this really relevant? Or is there similar physics? And the answer is yes. Well, simplified, these linear devices have the necessary gradients to drive instability similar to a tokamak. So plasmas flow like a fluid. And so you can get a fluid instability called the Kelvin-Helmholtz, which if you haven't heard of, is you're all at least peripherally aware of, because this is what causes ocean waves. This is also, if you're lucky enough, I took this off Google. I always stare at the sky trying to see these, but you can get waves in the sky. And again, this is just different density gases or fluids. And you get a slight perturbation and it leads to these roll-ups. There's something called a drift wave instability I won't go into. It's, as far as I know, this is unique to plasmas only. There might be analogs in other media, but I'm not aware of them. And then the last one that's really common is called the Rayleigh-Taylor instability, which you've all probably heard of, or you're at least again familiar of. If you ever try and put a heavy liquid on top of a light liquid, like what's happening down in this wine glass where they put the colored food droplets in water and watch it sink, that is the Rayleigh-Taylor instability. So these same instabilities exist in tokamaks, and they exist in a linear device. So while we can't study all the instabilities of a tokamak, we can study these three and try and understand how we can control them and change them. And so that's what my dissertation was on. It turns out because plasmas are these positively charged and negatively charged particles, you can use things like electrical charges or electrical biasing to have an effect on your system. And so I put in a series of electrodes and played with putting some sort of voltage on them. And so you can see down here, I have what are called these spectrograms. So all this is if you've heard of a Fourier transform, this is a 2D depiction of a Fourier transform over a large space where I was changing some voltage, and then the Fourier transform frequency is plotted on one axis, and then the color bar indicates the level of that Fourier transform signal. And so anywhere where you see these really bright orange places is where there's some sort of instability happening. So if you have a single one like this is what we call a single mode instability. And you can see these other peaks as you go up are called harmonics, and they just happen because if this was a pure sinusoidal wave and you took the Fourier transform, you'd have a single peak. If it's not purely sinusoidal, then you get what are called harmonics. And then we could also go to this case where now I just have this sea of bright orange, and that's because I didn't have a single mode. I had tons of different modes all intermixed. And this is what somebody might dub as turbulent, or as we called it to be very careful, is broadband turbulence. And so we could create these different instability regimes in this device and study what changed, what caused them, and then you can see that there are cases where I was able to get rid of them. And could we understand that? And then somebody can maybe take those techniques and apply them to a tokamak to try and make fusion energy work better. And then, of course, at some point you have to graduate again. And for those of you who are in grad school, or even if you're an undergraduate, you might also be having this, like, these nervous jitters of what comes next. And if you're getting, an advanced degree, you might be thinking, even undergraduates, if you want to teach high school, or if you want to go on and think about getting an advanced degree, do I want to teach? What about industry, right? There's a lot of industry jobs out there. What's it like to work in industry? And then, of course, there's always the National Laboratory, where I'm at now. And because this is a women's talk, we'll talk about, one of the elephants that I feel like always comes up, which is, what about the family? It's a pretty big commitment on typically a woman's part to decide that she wants to have kids. And so how do you balance all that? And I can't speak for all of these. I did teaching. I was a teaching assistant in graduate school. Teaching was okay. I didn't love it. I didn't absolutely hate it, but it wasn't my passion. And I do feel like teaching is something you have to have at least a bit of passion for. And that left me mostly with these last three. I am one of those women who hasn't ever wanted a family. I'll be honest, kids kind of freak me out. I'm told it might change as I get older, but I'm more than happy to be aunt to my best friend's cute little girl. And but there are lots of women who have families, and some of them do it before graduate school, do it during graduate school, do it after graduate school. And it's a really hard decision that there is no right answer for except for whatever works best for you. And, that left me, personally, with industry and the national labs. And so when you're trying to decide these things, trying to figure out how you meet people, my one advice is, if you're going to conferences, network. I have since learned that not all conferences have good poster sessions, which makes me really sad, because the conference I always went to in grad school had an amazing poster session, and I met so many people, not just that came to see my poster, but I went and saw their posters to know what, there was industry people there showing posters, so I could go see what their job was, and did I want to work there? And so conferences can be a great place. Some of them even have job fairs or places to do job listings. Universities often have job fairs. Go to all of these. And I'm going to tell you, apply for and take interviews for jobs you don't think you'll say yes to. And this is my biggest advice to you, because if you had asked me in graduate school if I was going to work for a national lab, my answer was vehemently no. I was not even going to apply for a national lab job. I wanted nothing to do with it. I didn't want to have to worry about getting a clearance. I didn't want to have to worry about ever working on classified material and not being able to talk about what I did. I didn't want to have anything to do with nuclear weapons. I did not want to work for a national lab. And then a very good friend, who was the same friend who introduced me to Mark Gilmore, had graduated a couple years before me. She had just converted to staff at Los Alamos, and we were at the same conference. And she said, "Hey, my team is having a lunch for potential postdocs." And I was like, "But I don't want to work for LANL. And she said, no, don't worry about it. It's free lunch. Just go for free lunch. And this may be the smartest and most devious thing she's ever done to me, because I was like, well, you know, free lunch as a grad student. Yeah, of course I'm going to come for free lunch. And I absolutely loved every person I met at that lunch. I loved the research that they did. It had nothing to do with weapons. None of it was classified. They could tell me what they were doing. It was nothing like the impression that I had of what working at a national lab would be like. And I found myself interviewing for them. And I also interviewed for what I thought was my dream job in industry for a private fusion company. And they both made me offers. And against everything I thought would happen, I took the job at the place I said I would never work. And I turned down the job I was most excited to have an interview for. Because in the end, when I went and interviewed at the industry job, I didn't like it. I didn't like the vibe. The people were okay. I wasn't as excited about the science when they actually described what my job was going to be. And I realized that it just wasn't for me. And it was against all my own expectations. So take risks, do things, you know, it never hurts to interview and find out what you might be missing. Because it might turn out that the thing you're going to miss is going to be the thing that's best for you. And in the end, what you really need to do, whatever you're trying to decide, is look at all your options and choose what is best for you. Don't let somebody else tell you that, oh, this is where you need to go. Just make as many options for yourself as you can and try it. And in the end, you know, if you don't like your job at one place, you can, these days with 401ks, it is somewhat easy to change jobs too. So, on to my postdoc work, and I am at my 45 minutes. So I will try and make these next few bits quick. So my postdoc work took me to the other side of fusion, back to inertial confinement fusion. And so in this case, we just need to briefly talk about what is a high energy density system. And these are described very confusingly as systems that have pressures above a megabar or energy densities above 100 gigajoules per meter cubed. And I'll be honest, the megabar we can put in more normal terms. I'm not sure about the energy densities, but this is how they are dictionarily described. And really, I find that this thought helps the most, where, you know, what we're really looking at is the center of the sun, where it's really hot and dense. We're looking at gamma ray bursts. We're looking at things that happened during the Big Bang. I don't remember what supernova progenitors are, but we're looking at very hot, very dense material. And on Earth, you might be like, wow, how do we make things like this? Like that's hot like the center of the sun. And the answer to these are large user facilities are used to create high energy density experiments. And so in the United States, there are two of these, the Omega Laser Facility in Rochester, New York, and the NIF, or the National Ignition Facility at Livermore in California. And so I've tried to put some pictures on here for scale. I actually found this picture. This is the NIF chamber, where in the center of this, they put those millimeter-sized capsules that they impinge with 128 beams of 1 megajoule or greater energy onto that 1 millimeter-sized target to try and create fusion energy. Just really quick, so essentially this just shows what I said is inertial confinement fusion tries to take millimeter-sized capsules filled with deuterium and tritium, shrink them by a factor of 20 to 30, and then generate, and inside is the deuterium and tritium that creates the fusion. And so on NIF, what they actually use is these gold holons, where the lasers hit these gold holons, they generate radiation that shrinks the targets. On Omega, the laser beams directly hit the target. So slightly different processes. They each have their pros and cons. And this seems really simple, right? Why doesn't this work? Well, something disrupts the process. And at the end of the day, the answer to this really comes back to instabilities. ICF capsules have a lot of complications going on. So anytime a laser interacts with a material and turns it into a plasma, lasers and plasmas interact and create instabilities. This creates radiation. Radiation traveling through plasmas creates more instabilities. When the laser, so these capsules are solid when they start. When a laser hits that solid material, it generates shocks. Shocks rattling through materials can create instabilities. Your shell is compressing very quickly, creating a gravitational-like force. You have different density materials. Now you're getting some Rayleigh-Taylor mixing going. And then, of course, anytime you start creating instabilities, you start creating shear, velocity shears, which gives rise to Kelvin-Helmholtz. And so we're back to a lot of those same instabilities that I studied in graduate school. Only now they're in a millimeter-sized capsule, which is kind of crazy. So how do you diagnose this complicated system? Well, again, you go to a simplified experiment. In this case, we were interested in studying how the shock interacts with materials. And turns out if you have a density difference, so here we had a 100 milligram per cc foam versus a 1 gram per cc foam, and you cross a shock across this, it gives rise to an instability called the Rickmeyer-Meshkov instability, or the RMI. And so we want to understand how this instability forms. Does it become turbulent? And can we affect that at all? And then what do we do with those experimental results when we're done? And in the case at LANL, I just want to mention, since there might be some computer people, LANL actually does its own computing and has developed its own model for trying to model these processes called, I'm just going to call it the BHR mix model. It's the Besnard-Haro, and nope, not very good with the last names. And so our experimental results are intended to help validate this model, so then we can go model more complex things like the inside of supernova stars, as an example, or these complicated ICS capsules. So from these experiments, we obtain radiographic images. So we use X-rays that pass through the material, and depending on the material properties, you can get almost complete transmission of your X-rays or very few transmission of your X-rays. And we look for differences in this transmission and in the growth that occurs. And I have to give a really huge shout out to engineers who do this. This capsule is 1.5 millimeters long, 0.5 millimeter in diameter, and they, in this high density layer in the center here, they put these complicated profiles. And so we can look at these, what are called initial conditions, and look to see how the growth of this instability changes based on these initial conditions. And I want to point out that this work is still ongoing. Yeah, I did put my one paper on here for this, but really this is a long process. So to give you some idea of how high energy density experiments work, is you work with a user facility, which is mostly a lot of work in communication. And I learned more about giving a presentation in my 2 years of a postdoc than I ever learned in my 8 years as a graduate student. And so working with facilities require, to do these experiments, you need designers. So designers are people at Los Alamos who sit down and use these sophisticated codes to try and help us fine tune our experiments. We know the physics we want to look at. We have some idea for an experiment. We go to these guys and say, hey, can you run a simulation of this to tell me if I'm completely crazy or how I can get the best results out of this? We then take that fine-tuned experimental idea to a set of engineers who actually help us redesign the targets so they're buildable, and then they actually build these targets, which is amazing to me. And then you then have to run everything by the facility. You have to send them your target design. You have to send them your experimental plan. You have to tell them where the lasers are going to go, how much energy you're going to use, what diagnostics you're going to use, and they have all of the people there to help you. And then on a shot day, you show up in case anything goes wrong, but mostly you sit around and you wait for your data. So for R&D experiments, you do an experiment about once every 6 months. And then once your experiment is well developed, you might get data about every 3 months. And so on a mega shot day, you get about 10 to 15 sets of data. And on a niche shot there, you get about 1 to 3 sets of data. And that data are those images, and you try and do everything based off those images. And so while this work was interesting to me and the science was interesting, I once again found myself sitting behind a computer every day, which I wasn't very thrilled about. And so while I was during the last year of my postdoc, I started work with the extreme fluids team. And all of their work is on-site and hands-on, and we get to touch it. But I still continue studying the Rickmeyer-Meshkov instability. And so in this work, what we have instead of this large user facility with lasers is we have a traditional shock tube, mostly traditional shock tube. So this 7-meter tall tube that you see here has a pneumatic piston on top. We can launch shocks in air at velocities up to Mach 1.5, I don't remember. I'm going to guess it's about 500 meters per second. We normally launch shocks at about 430 meters per second, which is about Mach 1.3. And then we use gases in our experiment. And so we have air on top, I have SF6 on the bottom. I launch this shock across there, and I get to watch how this instability evolves. And so the R&D part of my work is what we want to do is study those same problems I was studying before, where engineers made these beautiful targets with great initial conditions, sinusoids and 3-dimensional sinusoidal shapes. How do you do that between two gases? This is an incredibly hard problem that I have now been studying for 3 years, and we have intermittent success. And so one way that we do this is you flow gas and you perturb it while it's flowing, and you see what kind of initial condition you get and hope that it's repeatable, or try to make it repeatable. Another method is to go to a solid structure. The problem with solid structures is they have to break easily. They have to not interfere with your diagnostics, and they have to not interfere with health and stability growth. So these are complicated and hard to do for different reasons. We use really sophisticated diagnostics with lasers, class 4 scary lasers that will destroy your eyes without proper protections. And so in one of our gases, we feed it with acetone. We hit it with a UV laser. This causes it to light up. And from this, we can get a density measurement. And then we also put in small particles, particle image velocimetry, and we do 2 laser pulses. Well, in our case, we do 2 laser pulses. There are different ways to do this. But the important part is you take multiple images separated by the delta T. You measure the displacement of your particles, and then the displacement over time gives you velocity. And so now we can get directly density and velocity measurements, which are the exact things that we need to validate the models that LANL is interested in validating. And so just to give a quick overview of the success we have had is that we have found differences with initial conditions, where by changing the initial condition, changing this profile, you get very different growth. So it's hard to tell exactly what this profile looks like up here. We give it this value called a Ka value, which just compares the wavelength and the amplitude. But essentially, you can see that at late times here, I still have something here that kind of looks like a sine wave. And as I go to the right, I start getting something more messy. So I'm starting to get something that looks more like turbulence. And what we want to understand is, why do some of these give us the sinusoidal shape, and why do some of these give us this turbulent shape? And then as an extension to these, LANL has this user facility called Krod, where we can actually now go to Mach numbers greater than 8. So this is getting us closer to that high density regime, but we're still in gases. And we use this very large gun barrel to launch shocks. And now we can use solid things because they break really small and even can disintegrate to try and do solid initial conditions similar to an ICF capsule. And then besides these experiments, we have 2 other ones that we do where we do particle tracking. We look at how shocks interact with particles to try and understand particle drag models. And then this other very cool one next to the VST is called the turbulent mixing tunnel. We have a pipe on top where we if you put fluid out of a pipe quick enough, you get a turbulent jet. And so we can study the long-term or steady state statistics of turbulence. And so on this experiment, they take 10,000 images of the same jet, and you average all of those together to start looking at what are called turbulence statistics, which is how we characterize turbulence and compare it to models. And then Nusrat was actually asking me earlier of, well, what's next? Am I going to stay at LANL? Am I going to go to one of the other national labs? And one of my friends tells me that, you know, there's a select number of people at the labs, decent number, where we just swap about every 5 to 10 years, people move between the different labs. So maybe. And at the moment, I'm happy where I'm at. I'm mostly happy with what I'm doing. And, you know, I'll worry about today, and tomorrow we will see what tomorrow is. And I just want to say thank you guys for being here. Sorry I ran long. I didn't know how to practice this to figure out where I could like parse down on things. And I also wanted to put a thank you to all of the different mentors I've had through all this work. They were all really great. They were all really supportive. And they all helped me get to where I am today, which is not anywhere of where I thought I was going to be in high school, and not even where I thought I was going to be in graduate school, or honestly, even as a postdoc. So thank you again. If you have questions, I'm happy to take questions. And yeah, that's all I've got.
Thank you very much, Tiffany. It is a great talk. And the floor is open for questions. If anyone has any questions, please feel free to unmute yourself, and or you can use the chat window.
Okay, let me break the ice here. So I will ask from the advisor's perspective. So, you know, in a research group, we have students who have different characteristics in terms of personality, in terms of where is their talent. I mean, other ones are better in theory, other ones are better in programming, other ones are better in hardware, in more hands-on stuff. So you as a graduate student and also as a postdoc, but also now from your position where you most probably collaborate also with interns, what do you think from your personal experience that it was like the best advice that you received as in your career as a student, let's say, and what do you think that you didn't like and you try to do it in a different way in order to support, I wouldn't say only, you know, women in engineering, but I will say in general, you know, young students, that they have the passion to continue either in research or industry?
So I think I'll try and answer the first. It's, you know, finding what you're good at is hard. I feel like I got, you know, maybe I got lucky. When I started working with Dr. Mark Gilmore, I had no hands-on experimental experience. I had grown up on a farm. You know, my dad built our house. So, you know, I came from a very hands-on background, but I didn't have any actual experience. And his group was really great about it, because they didn't feel, you know, they were shocked, but because they all came from a background with hands-on experience, but they were really nice about it. And it was really Mark who pushed me to keep being an experimentalist. You know, I, like many people and many women, have, you know, it's hard to look at it. You know, we're taught not to like really brag about what we're good about. And I didn't really see that I was good at it, but he did. And I remember I was going to get my master's and I was going to find a job, because it never occurred to me to get a PhD. And he kept pushing. He's like, you're too good. He's like, this is what you should be doing. You should be doing experiments. And at some point I realized just how much I loved it. And I was like, well, if I love it, then even if I'm not good at it, I can get good at it. You know, I knew I didn't love computer simulation, so I couldn't see myself ever being good at that. And I knew I didn't love the astrophysics version of data collection and analysis. So, and I do see this now, having some of my first students, trying to put them where they best belong. And these students come in, and the work that I do is extremely research and development. It is a lot of continuous failures. And I'll be honest that most of the postdocs I've worked with so far can't handle that very well. They have a very hard time with it. I can literally spend weeks and months beating my head off the same problem and making very little traction, and still go back the next day with mostly a smile on my face. It isn't to say it doesn't eventually wear down on me, but and for my postdocs so far, they get really discouraged by it, and which isn't to say that they shouldn't do it, but maybe there's a better fit in doing science that isn't quite so R&D. And we had one postdoc who the one who I showed his results at Mushtaba, he was, for me, like, what he did with data was amazing. He was really good at sitting down and analyzing it and researching papers and finding the best way to find the physics out of those. And so that, and I could see that was, that was really where he needed to be, was in a data analysis kind of position. And we've had postdocs who are just amazing at mathematical models. And so they still did experiments, but they sat down and figured out physical models to apply to their data. And so it really is trying things and finding out what you're good at. And maybe being lucky enough to have somebody, if you don't recognize yourself, to point out what it is you're good at and help you find the best fit of work for you to excel. And now I've forgotten the second part of your question.
Well, if you actually, I love the message that you gave, like try to find out what fits better your passion and what you love. If there is something that you as a student you wanted more help, or somebody to boost you more in something, if there is something, maybe there is nothing.
I mean, it wouldn't. So I guess for me, I came from an astrophysics background. So for me, like, my physics classes didn't have enough real world examples. And that was the thing I hated. And I often tell the story about my first day of as an electrical engineering PhD student, was in antennas class with Christos from the ECE department. And he did this long derivation. I was like, oh my God, this is like my physics classes all over again. And then I remember him like dusting his hands when he's done. He's like, okay, you never have to do that again. Let me tell you what this equation is useful for. Let me tell you how you're going to apply this. And so for me, I think that was what, from a schooling point of view, that was what I didn't like the most about my physics classes, is they were too theoretical. There wasn't enough, like, I like real world examples. I like to know how this is, like, and I see this in talks where people give talks where they don't tell me the motivation for their work, and their talk means nothing to me, because why should I care about this problem? Is it really important to me? And that was the thing I was most disgruntled with in physics. And that's why I got out of technically physics for my graduate degree and went to electrical engineering, is because I needed that application. And so I wish my earlier classes had more application, but I think that was more a fault with the degree programs I had chosen rather than the fault of the schooling itself.
Excellent. Thank you so much, Tiffany. Thank you. It was great having you here tonight.
This is. I wish that I had maybe there were talks like this when I was in graduate school or undergrad, and I just never paid attention to them. But I hope it helps people. So, and I think I see a hand up.
Thank you, Tiffany. So I see there are two questions in the chat window. Oh, Karen, you can speak up. Karen is here. You remember Karen, Tiffany? So,
yeah, I thought that was Karen, but I wasn't sure.
Okay, Karen, do you want to
do you have
speak up or do you want me to read? Okay.
I actually have the chat up. I did read it. So my answer is there are lots of if you wanted to at LANL, you could spend your entire day going from talk to talk. That almost every group and team gives regular talks. And so there's lots of opportunities to view work that other people are working on. LANL also has an internal system where when we do things like talks like this, that we have to pass, I had to pass it through a classification review. And depending on the settings that people set to those, you can always haunt those and go pull down people's recent presentations and see what people are up to. You'll get a random, you won't have much control over what you get in that one. But there are lots of talks where people come and give updates on their work. There are working groups. If you have an idea for a project that like, especially as an experimentalist, I really want to collaborate with simulation people because that's where my work is relevant. So there are working groups where you can go to and meet these people and talk to them, and you can collaborate on projects together. I talked about that ongoing work for my postdoc. We actually have a collaboration with that group. LANL has what are called milestones, where they have a set problem. People and groups are hired on to try and solve that problem, and then we have to give updates. And so we're on the same milestone together, where we're working, because we are working on the same problem, just they're in high energy density, we're in a traditional gas or fluid. And so we're tackling this problem from two different sides. And so we're sharing our results, we're talking to each other. So collaboration is pretty easy. Changing groups can be equally easy. People do internal job ads, and you can also apply to the external job ads. And so you can apply to one of those jobs, you can go and interview, and you can change groups just that easy if you get the job. A lot of people end up changing groups if they decide they want to do management. They'll apply. So there's a very complicated hierarchy at LANL, but essentially every group has a group leader and a division group leader. And so lots of people will change groups by going and applying for one of those positions for a group they know nothing about. And that's how they go and learn about that group. One of the mentors I mentioned on this thank you slide, Kathy Prestridge, she's been doing experiments at LANL since she came as a postdoc. I want to say she's been there like 20, maybe 30 years. She just decided she wanted to learn more about simulations. She just transferred to the simulation group. We are absolutely encouraged to collaborate. It's looked upon very well. We do performance goals every year. And one of the things that we can fill in our performance is how much collaboration was done with other people. And in your last question, I kind of still have mentors, and that's actually more by choice. So LANL is trying to be better about mentoring early career scientists. But I have had the pleasure of having met so many great people that I didn't feel like I needed a specific mentor. If there's something I'm confused on, I pretty much just show up in somebody's office and ask them questions, and nobody has kicked me out yet. So everybody's pretty helpful and pretty great.
There is another question. Yeah, there is another question.
From Tristan. Okay. So I'm going to answer this with I don't think so. So for people who can't read the question, they're asking about whether I've had struggles with people viewing me as less credible because I am a woman in STEM, personal or professional. The one personal case I remember is the one from high school. I will admit that I am pretty oblivious unless people are very direct with me about these things. So this isn't to say this hasn't happened. It's just to say that if it's happened, I've been oblivious to it. I have run into some disrespect from older generation males. Not so much about my research, but just in conversation where they've met me 3 or 4 times and don't remember they've met me. Or my favorite one was being in a WebEx and the guy still called me the wrong name 3 times, even though my name is on the screen. My name was not important enough for him to read. And I happen to know from talking to other women that he can be quite disrespectful to women. But beyond that, I don't think that I've experienced it, but again, beyond those couple of examples that come to my mind, but again, I am pretty oblivious unless it's very obvious.
Thank you, Tiffany. We have someone raised hand. Yes, please feel free to unmute yourself and ask question. Aisha Rahman.
Hello, can you hear me?
Yes, we can hear you.
Hi, it was a very good discussion and was very inspiring. I really like the fact that you said that if I love something and even I'm not good with it, I'm gonna get good because you love it. So I'm a new graduate student and I just joined recently. So my question is the fact that you mentioned that there were days when you didn't have to do anything but to look into some pictures and you were waiting for results. And there were days when you didn't have any results. For a very long time, you didn't have any results. So I want to ask, what kept you doing it? What kept you going through it? Because at the beginning, you didn't know whether you loved it or not. So yeah,
That is a great question. So those days mostly happened for me as a summer intern. And you know, as a summer intern, I would say your motivation is, well, I'm getting paid and I don't have anything better to do, so I've just got to tough this out and hopefully it turns out okay. As a graduate student, I would say that's probably a pretty, I could see there where that would be a really hard position to be. And not knowing your circumstances or your group, you know, when I first joined my graduate group, I didn't know, I mean, I remember we had a circuit that was broken. The guy handed it to me and said, hey, can you go fix this now? So I was like, sure. How do I solder? And I remember he just stopped and stared at me and went, okay, let's go teach you how to solder. And so I spent a lot of my early time in that group when I hadn't gotten to do my own experiments and have my own data. If people were okay with it, shadowing them and watching them do their experiments and asking them questions and learning about the physics that they were studying. You know, and I always hate to tell people, like, I personally am not a huge fan of reading scientific papers unless I have a purpose in it. You know, reading it because I need to solve the mystery of what's happening to my experiment, or I need to learn how to do some sort of technique to analyze my data. I get a lot out of reading papers for that, but reading papers just to try and learn, I tend to find I don't have really good memory retention. But that's also you know, something else I know a lot of groups will recommend is go try and read some papers on it and maybe expand your knowledge on the subject a little bit and see if you actually even like learning about the subject from that kind of point of view. You know, I may not always remember the information I read in some of the turbulence papers I read, but I almost always learn something fascinating still. It actually led to me writing a proposal for a specific project of work. I don't remember a lot of details about the paper, but I got one crazy idea for an experiment. And so I wrote a proposal in it. So that's also something else you can do, which, you know, I always kind of feel like I'm telling people to go do busy work when I tell them just go read papers. But if you have people in your group that you can shadow or look over their shoulders, or maybe they have data that you can, that's similar enough to what you're going to be analyzing. And so you might analyze it not because maybe they need the help or want the help, but just because it's an opportunity for you to learn, and you can compare the results with theirs and see like, okay, am I doing this correctly? And so that might be some ideas that both benefit you, but might also help you try to decide if you like what you're doing.
Thank you, Tiffany. Any other questions from audience, please?
I have one question. I put in the chat, but I had a question. You mentioned conferences, and I couldn't agree more that conferences are so important. I was wondering, what conferences did you attend? Yeah, because like some of them do not have good poster sessions. So I was just curious.
So in graduate school, I attended the big conference we attended with lots of people that had an amazing poster session. Is the American Physical Society Division of Plasma Physics, APS-DPP. And they have 2 poster sessions every day of the conference. It runs for 3 or 4 hours that you have to stand, that you're supposed to stand at your poster, and so people can come by and talk to you. And so that's what, and I had assumed like every conference, every APS conference had a poster session like that. The other conference that I often attended in graduate school was a very targeted conference. That one was called TTF, which is the Transport Task Force. It's all about turbulence and tokamaks, very specialized. That one, we did still have a poster session. It was very well attended. It's a small conference, only about 50 people attended it. And so they took like an hour or 2 hour chunk out of the day where we didn't have any talks. So the only thing for people to do was to come see the posters. In graduate school, I still went to APS-DPP, or sorry, not in graduate school, sorry, as a postdoc, I still went to APS-DPP. And then there was another specialized one, and I can't remember what it's called because I only went to it once. Actually, there's a couple specialized ones. So the one I can't remember the name of, it's only for inertial confinement fusion, instabilities and inertial confinement fusion.
Is it ICOPS, Tiffany?
No, it's not ICOPS. I forgot about ICOPS actually. No, it's a small one. I think we were like 35 people at that conference. It's incredibly small. It's probably the smallest conference I've ever been to. And so in that one, people submit abstracts and they decide whether you do a poster or whether you do a talk. And again, for the poster session, they don't do anything else at the time but the posters. And then probably my favorite small one I go to these days is a turbulence conference called the International Workshop on Compressible Turbulence or something like that. It's got a really crazy IWPCTM. It's got a really crazy name and acronym. They don't have, like, people do posters, but nobody really goes and looks at them. So that's one where they do it, but it's like people put them up and they're there all week or the 3 or 4 days of the conference. But there's never really like any set aside time where people can like people just doing, oh, we're on break, and I guess I'll go stare at a poster, and maybe the person that's in the room that did the poster will walk over and talk to you about it. And then my big one I go to is now APS DFD, which is Division of Fluid Dynamics. And if you have not been to this conference, it's a monster. I did not know how varied fluid dynamics and the study of fluids is until this conference. And their poster session is pretty much non-existent, and almost nobody does it. And probably my biggest disappointment with it is they also don't do any sort of job fair. So I've talked to a lot of people, graduate students in fluid dynamics, who don't know how to find jobs because this is the only conference they come to. There is so much you can do with fluids. I think they typically have something like 15 sessions, maybe 20 sessions going at a time. We start at 7:30 in the morning, we end at 7:30 p.m. at night. And there's technically a lunch period, but there's usually workshops going on. So it's incredibly difficult for graduate students to meet people at that conference. And it's definitely a conversation a lot of us early career staff have been talking about, is how do we fix this problem for those graduate students? And so yeah, those are all the different types of conferences I've gone to. And so I've been to ones where there's like DPP holds a job fair. They, people from industry and the national lab show up to hire, like they interview people on site at the conference. They have a database where people can put in their resumes. And at the other end of the spectrum, you've got DFE, where I don't even know if they have a place to submit resumes, and no really good way for people to post their jobs or for students to find jobs. And I know what a lot of them do is, there's a lot of listservs these days where people post their jobs. I think APS has a job forum where you can post your resume too. But it can definitely be a really big problem if your conference doesn't support it. And I would say that if you're, no matter actually where you're at in your career, if there's a single conference you go to, try and find out who the organizing committee is and send them an email and be like, hey guys, like maybe you guys don't realize that this is a problem and we need some forum for this. And it was one of my friends who they actually started at DPP. It was really a graduate support group is what they had started, but they went to the organizing committee and said, hey, we want to start this. And we want a chunk of time during every conference where students can just show up and talk to each other and be a support for each other. And some organizing committees maybe they'll set aside a lunch hour or something that can be devoted to people looking for people to hire and things like that. So I don't know if that's really inspiring or hopeful, but yeah, it can definitely be a problem. Not all conferences really take that into consideration.
Yeah, no, thank you for the advice. That was very informative.
Okay,
I
thank
will
you.
also say,
oh yeah, sorry, go ahead.
Sorry, I just want to add to that. Sorry, this popped in my head. It was on one of my slides, but I think I was kind of rushing through. So my friend ran into this problem actually when she was looking for graduate schools. She came from a very small university and was having trouble figuring out where to apply to. And so during her presentation, she put a blurb at the end saying, hey, I am graduating and I want to go to graduate school. Come talk to me about your program. And that's actually how she ended up in her graduate program, is somebody saw that. And so they went and tracked her down and talked to her. And so it never hurts. I'm going to self-promote yourself. And I will tell you feel free to just email, like if you see some talk, go up and talk, and you think their work is cool, go up and talk to them, or send them an email and say, hey, I saw your talk and your work sounds fascinating. Are you looking for students, or are you hiring? So just an added last 2 cents there.
So Tiffany, would you mind to take one more last question? I think it's in the chat window.
Okay. Okay, at what point? I would say there is no wrong point ever to become involved in a professional organization. If nothing else, professional organizations give you the opportunity to meet other people in the field, whether they're more experienced than you, as experienced or less experienced. I think there's always something to be gained to be talking to other people in your field. And so if you are a freshman and you don't know what you're going to like, I would go and see what people are working on. As far as I know, UNMECE still requires all the seniors to do an honors project. So maybe you'll hear people talking about their honors projects. Maybe you'll hear them talking about, oh, hey, I'm working with such and such professor in this lab and he's hiring more people. Or maybe you'll hear about such and such, you know, if they have like outside people come in, you might learn that such and such is hiring summer interns at some other university and will pay for you to go and work there for the summer. So I would say that there is never a wrong time to join. I wish I had done it sooner. I wish I had talked to people sooner. And so I would say just go for it. And the benefit is networking is absolutely important. Even if you don't work for somebody, you know, maybe someday they become a collaborator. Maybe someday you know, if you become a professor, you send your grad students to them and they send their grad students back to you. There are so many reasons to try and network within engineering and science that I would say just do it. It's, you know, and it can be scary, but just do it.
Okay, thank you again, Dr. Tiffany, and audience. Once again, many thanks for your presence and interest tonight to make this event successful. This monthly talk actually is a great platform for the students who wants to pursue career in STEM, make connections, and you get answers that you probably wonder always. I enjoy running this role very much. Thank you all again for your support. If anyone is interested in running administrative role, feel free to email me. We have a couple of positions available. And of course, we would like to express our gratitude to our Albuquerque IEEE section, as always, for their support to make this event successful. With that, I hope to see you all in next month. Thank you again. Before we end, is there any other final words that anybody wants to add anything? Okay, if not, then let's thank our speaker one more time. It's a virtual. So we will, yeah, so we will hang out here. Sure, we will hang out here for a few minutes, so you can stay if you want to talk to the speaker. Otherwise, you all have a wonderful night.